Now we're going to look at the second derivative test, which gives us another way to determine where we have a maximum or a minimum. So remember, our maximum and minimums occur when the derivative is 0. So both of these assume that you've got a point where the derivative is equal to 0. Okay. Now by looking at the second derivative, we can decide if it's a minimum or a maximum. So if the second derivative is negative, okay, then we have a maximum point at A. So what this is saying, if you know you have a minimum and maximum, and the second derivative being negative means you're concave down. So you can think about being concave down. That would give you a maximum. Okay, and the second part's just the opposite of that. If you have a place where the derivative is 0 and the second derivative is positive, then you're going to have a minimum point. So the second derivative being positive means that you're concave up. So we would have a minimum point. Okay, so this says for the following functions, find where f of x is increasing and decreasing, where f of x is concave up and concave down, any inflection points, and any maximums or minimums. So we're going to use the first derivative and the second derivative to find out as much as we can about the function. So here we have f of x equals x squared minus 4x plus 3. So the derivative would be 2x minus 4, and the second derivative would be 2. Okay. Now, the second derivative is always positive, since it's always 2. So this entire graph is concave up. Okay. So you can say f of x is always concave up. Now, since it's always concave up and it's never switching concavity, we have no inflection points. Okay, now let's go back to the first derivative. If we set that equal to 0, we're going to get x equals 2. Okay, so we have a critical point at 2, and if we make our first derivative sign chart, okay, if we plug in something less than 2, if we plug in 0, we're going to get negative 4, so it'll be negative, and plug in 3, we get 2, so that's positive. So this tells us that f of x is decreasing from negative infinity, or we can say on this interval, to 2, and f of x is increasing from 2 to infinity. Now we have the information that the second derivative is positive, so that means we're concave up. Okay, so since we're concave up at 2, we have a minimum. And to get the minimum, remember we find f of 2, so we plug 2 in here. So 4 minus 8 would be negative 4, plus 3 would be negative 1. So it has a minimum of negative 1 at x equals 2. Okay, so we've really given all the information we asked for. We said where it was increasing and where it was decreasing. We said that it was always concave up. It didn't have any inflection points, and we had our minimum of negative 1 at 2. Okay, let's look at another example. Here we have f of x equals x squared minus 3 over x minus 2. Okay, so to do our derivative, we're going to have to do the quotient rule. So low d high minus high d low all over low squared. Now this is one of those cases where to solve everything else we need to do, we're going to want to simplify this. So distributing the 2x, we'd have 2x squared minus 4x, and then distributing this negative 1, we'd have negative minus x squared plus 3. this is going to give us x squared minus 4x plus 3. Now, to find any critical points so that we can do our first derivative, we're going to put 2 on here where the function's undefined because things could change. But then we also want the zeros, which would be the zeros of the numerator, which this will factor as x minus 3 and x minus 1. So we'll put 1 and 3 here on as well. So I'm going to put a 0 above those so we know that those are where it's 0 and this is where it's undefined. And we can go ahead and fill that out if we want. So if we plug in 0, we know the denominator is always going to be positive because we're squaring it. So we can actually just look at the sign of the top. If we plug in 0, we'd get positive 3, so this would be positive. Now it might be helpful to use our calculator since this does get a little more complicated. So our first derivative here, we've got x squared minus 4x plus 3 divided by x minus 2 squared. So if we go to our table, so if I put in 1.5, it's negative, so the next one will be negative. If I put in 2.5, it's going to be negative. And if I put in something like 4, it's going to be positive. So we're going to have negative, negative, positive. Okay, so this tells us that f of x is increasing from negative infinity to 1 and from 3 to infinity, and f of x is decreasing from 1 to 2 and then from 2 to 3. Now next we're going to need our second derivative, which means we're going to have to take the derivative of this. So second derivative, we would have low d high minus high d low, which will be 2 times x minus 1, all over low squared. Okay, so I'm going to pause this and do a little bit of algebra to simplify this, but I don't need to take your time showing you all the steps. I'm going to square this, FOIL it out, distribute this. I'm basically just going to simplify the numerator. Okay, so this simplifies down to negative 2x squared plus 10x minus 10. Okay, so we can now make a second derivative sign chart, and we're going to put 2 on here since it is undefined there. But then we'll also want to put the zeros of the numerator. Now the numerator unfortunately doesn't factor, and so what the zeros of the numerator are, if you do the quadratic formula, it's 5 plus or minus the square root of 5 all over 2. Now to kind of give us some sort of reference point, I think, to go on, we'll do 5 plus the square root of 5 over 2. So that's about 3.6, and 5 minus the square root of 5 all of that over 2 is 1.4. Okay, so we know we'll want to put 5 minus the square root of 5 to here, 5 square root of 5 over 2 here. Now, if we put in 0 to our second derivative, we're going to get negative 10 over a positive number since it's to the fourth. So this is going to be negative. Remember the negative one was about 1.3. So this is where we're going to want to put the second derivative in our y equals to help us out. Go to the table, and we need something bigger than 1.38. So 1.5 will work, so that's positive. Then we need something between 2 and 3 something, so 2.5 will work, that's positive again. And then we need a bigger number like 4, and it's negative, so it's going to go positive, negative. Okay, so what this tells us is that f of x is concave down on the interval from negative infinity to 5 minus the square root of 5 over 2, and from 5 plus the square root of 5 over 2, and f of x is concave up at, so from 5 negative square root of 5 over 2 to 2, and from 2 to 5 plus square root of 5 over 2. Now we have inflection points where we're changing concavity, so where we're changing from negative to positive. So we have inflection points at, so the x value will be 5 minus the square root of 5 over 2, and then to get the y value, we'll plug this into f of x, into the original. So if we put our original in y equals, and go to our table. So we can actually do 5 minus the square root of 5 over 2, and we'll just take an approximation here. We'll say this is about 1.76, and then we'll do 5 plus the square root of 5 over 2, so 6.24. Okay, now the one thing we haven't done are any minimums or maximums. So here at 1, we have a min or a max, and we can see that's going to fall in here. So since we're concave down, it's going to be a maximum. So we have f of x has a max at 1, or I guess we'll say of the y value when we plug 1 into the original, which is what we already had in there. So 1, our max is at 2. At x equals 1. Let's see the other place where we had a 0. It was at 3. So at 3, we're here, and we're concave up, which means we have a minimum. So f of x has a minimum 6 at x equals 3. Now, you may be wondering, how can this minimum be bigger than our maximum? And remember, these are local mins and maxes. So if we look at the graph, so we're saying, so that's an asymptote. This is a local minimum because it's the lowest point. It just happens to be higher on the graph than this point right here is our local maximum. Okay, so that's why we can talk about local versus absolute or global. So this graph doesn't have any global max or mins, but right here we found at 1, 2 we found this local max, and at 3, 6 we found this local min.